Image formation rules for spherical mirrors. Before we delve into the rules that govern the formation of images in these mirrors, let's recall the definition of an image from yesteryears. An image is a point where the rays of light coming from a point on the object meet or appear to meet after reflection or refraction. This implies that we need at least two rays to work with when working out the location of the image. Fortunately, spheres have some geometrical properties which allow us to use a small set of special rays, which we call principal rays, to determine how images will form. Let's look at these rays one by one. A ray parallel to the principal axis after reflection will pass through the principal focus in the case of a concave mirror, or appear to diverge from the principal focus in the case of a convex mirror. Next, a ray passing through the principal focus of a concave mirror, or a ray which is directed towards the principal focus of a convex mirror, will after reflection emerge parallel to the principal axis. Next, a ray passing through the center of curvature of a concave mirror, or directed in the direction of the center of curvature of a convex mirror, will after reflection be reflected back along the same path. Next, a ray incident obliquely to the principal axis towards a point P, the pole of the mirror, on a concave mirror or a convex mirror will be reflected obliquely. The incident and reflected rays follow the laws of reflection at the point of incidence, the point P, and make equal angles with the principal axis. Having seen these important results, let us apply the same set of rules for convex mirrors. The only real difference between convex and concave mirrors is that all the real points in a concave mirror are replaced by virtual points in a convex mirror. A convex mirror is always divergent and as a result will always form virtual images. What does this mean? The rays will always diverge away from the mirror after they are incident on the mirror, no matter where the object is kept. This means that the rays always seem to be originating from some fictitious virtual point behind the mirror, and the image that we see will always be virtual and diminished. Now, let's look at the various cases for concave mirrors. Case 1. The object is at infinity. When the object is at infinity, what does this mean? It simply means that all the rays coming from this object are parallel to each other. In this case, after reflection, all of these rays will pass through the principal focus of this mirror, and the image that we get will be real and highly diminished. Case 2. The object is at a point beyond the center of curvature but not at infinity. Now you may ask, sir, how is this different from case 1? Isn't the object beyond the center of curvature in both cases? True. The important difference here is that in this case, the second case, the rays are no longer parallel to each other. The rays are now forming an angle with each other. If you look at the principal rays originating from any given point on the object, one of those rays will travel parallel to the principal axis and of course be reflected through the focus. Another ray will travel through the center of curvature and be reflected straight back, and another ray which passes through the principal focus will be reflected parallel to the principal axis. If you look at the point where these rays intersect, you now have the image point for this case. Notice that the image is inverted. It is upside down. And since the rays are meeting at a real point in space, the image will also be real. And it will be smaller than the size of the object. Case 3. The object is at the center of curvature. Again, taking two principal rays, if we observe the behavior of these rays after reflection, we notice that they are intersecting at a point that is at the same distance as the object's distance from the mirror. So in this case, the image will form at the same point where the object is placed. Also, the image will be inverted. It will be real because the rays are meeting at a real point in space, and it will have the same size as the object. The image and the object will have the same size. The next case, the object has been placed at a point between the center of curvature and the focus. In this case, if you take two principal rays and observe how they intersect beyond, you will notice that we now have a magnified image which is real and inverted. Next, the object is at the focus. You can consider this to be the converse of the first case. In the first case, the object was at infinity and the image was being formed at the focus. Here, the object has been placed at the focus. All the rays coming from this object will strike the mirror and be reflected parallel to each other. Since these rays are being reflected parallel to each other, they are not going to meet. But please note, neither are these rays diverging. They are not going to meet, but they are also not diverging. We tend to see that parallel lines intersect at infinity. So we can say that the image in this case will be formed at infinity. The next case, the object is between the focus and the pole. Now in this case, we see something interesting. If you observe the behavior of the principal rays, you will notice that after reflection, they are diverging from each other. This means that they will never meet in front of the concave mirror, but they seem to be originating from some fictitious point behind the concave mirror. This is the one case in a concave mirror where the image will be erect, magnified and virtual. Image formation in convex mirrors. Since convex mirrors are always divergent, image formation in such mirrors has fewer variations of cases. These mirrors always form virtual diminished images. If the object is at infinity, the image point will be at the focus behind the mirror. And for all other locations, the image will form between the pole and the focus of the mirror. A convex mirror is by design incapable of giving you a real image.